Okay, so I want to show that C is not path connected. What was C? C is this. Okay, I want to show that this is not path connected, and we will prove it this way. I'll take these 2 points, the origin, or maybe we use a different color. Okay, seçelim. This point 0 0 and the point 1 over pi 0. 1 over pi 0 is okay, I don't know where is 1 over pi. Somewhere here, I guess. Right. 1 over pi'den sonra bunun sıfır var mı? 2 over 1 over pi'den daha büyük bir sayıda tersini aldığımız için aslında 1 over pi sanki şu, değil mi? Yanılıyor muyum? Bir daha sıfır olmuyor bu. Sinüs pi. Evet. 1 over pi bu point. Okay. Şimdi diyelim ki assume that C is path connected. Path connected means any 2 points of C can be joined by a path. Assume that I want to join this point and this point by a path. All right, so let's see. Assume on the contrary that C is path connected. Path connected. And gamma 0 1 to C is a path with, let's see, gamma 0 is the origin and gamma 1 is 1 over pi 0. Okay, so I have a path joining this point to this point. Of course, I cannot draw the image of that path because actually it doesn't exist, right? I'm just trying to show that it doesn't exist by contradiction method. Okay. All right. Now let gamma t has the coordinates xt and yt, right? Gamma is a function from real line is 0 1 into c, where c lies inside R2, right? Therefore, it has 2 coordinates x and y, and let me just denote the coordinates of gamma by xt and yt, where both these are x and y, xt and yt are real valued continuous functions, because gamma is continuous on 0 1. Okay. All right. Moreover, since gamma 0, which is x0, y0 is 0 0, and gamma 1 which is x1, y1, and this is 1 over pi 0. We see that uh, x of 0 is 0 and x of 1 is 1 over pi. Okay. All right. Now uh, the subset. Okay, since x is continuous, the subset x inverse of 0 infinite, inverse image of 0 infinite is open and contains 1, because the image of 1 is 1 over pi, and it's a positive number, and uh, 0 is not here, because image of 0 is 0 and 0 is not in the open interval 0 infinite, right? This is the open interval. Okay. Well, so I have this. Let me draw. Here is 0, here is 1. X inverse of 0 infinite, x inverse of 0 infinite is an open set containing this point, and it doesn't contain 0. Well, since this is an open set containing this point, there is an open ball I can draw around this, which lies inside this open set. Open ball, of course, in the interval 0, 1. So it means it's an open ball like this. Okay, A1. Let me choose this A. Okay, so uh, okay, choose a maximal so that A1 lies inside this open set. I can certainly do this. There is at least one such A. Just consider the set of all such A's and take their supremum, infimum. This A cannot go to minus infinity because 0 is not in the set, so I cannot go up to 0 even. I have to stop somewhere here. So I just take smallest A so that A1 belongs to this gadget. Okay, and this uh, point here has to be like this. It cannot be like that, because if it were, then since this is open, I can draw another ball around this and take A even further to the left, right? So it should be really an open interval like this, because this is an open set also. All right. Well, in this case, hence, or this implies uh, x of A uh, is 0. Why is that? Because if it were positive, then uh, otherwise x of A would be positive, and since this is positive, you see, if a function is positive at some point, then there is an interval like this. and on this interval it is still positive. Therefore, this function would be positive on a point which is smaller, at a point which is smaller than a. But a is smallest. Well, I said maximal, but smallest. Choose a minimal. Okay, so there would be another point which is less than a, and at that point x is still positive. Therefore, this should be 0, and this would imply this would contradict to the minimality of a. Okay, uh, since x is continuous. A continuous function, if it is positive at some point, then it is positive in a neighborhood containing that point, and that would mean that x would be positive uh, at some points which are smaller than a. But that's a contradiction, because we choose a to be minimal with that property. Okay. All right. What else? Well, then we have the following. This a is between, of course, 0 and 1. A could be 0. Okay. And x of a is 0. Yes. Now, here is a and here is 1. Take any t here. Then, since t is in a1 and a1 is in the inverse image of 0 infinite, we see that xt is positive. Okay, xt is positive. Then we write the following. Finally, consider this y of a. So I look at the value of the second component of gamma, right? Gamma has two components. Gamma has two components, x and y. I look at the second component of gamma, which is yt, evaluated at a. This is equal to limit of yt as t approaches to a from right. So as I approach a from right, this limit is equal to this, because gamma is continuous. Therefore, both x and y coordinates of gamma are continuous. But you see, uh, t is a positive number because t is larger than a, right? T is approaching to a from right means t is larger than a. But a is at least 0, therefore t is positive. When t is positive, right? When t is positive, then, okay, you are here, right? When t is positive, you are here on the blue curve. Therefore, the y coordinate is just sine 1 over the x coordinate. Therefore, I can write this. So this y coordinate is nothing but, this is just sine 1 over xt. Okay. Well, as t goes to 0, of course, t goes to a, xt just approaches to 0. So this is a contradiction because t goes to a and x is a continuous function, so this goes to zeros, 1 over 0, and sine of that, this limit doesn't exist. A contradiction, since the limit as x goes to 0, sine 1 over x doesn't exist. Okay. As t goes to a, this goes to 0, therefore this limit would be this limit, but this limit doesn't exist. However, on the other hand, it exists, and that's a contradiction. And we arrived at this contradiction since we assume that the topologist sine curve is path connected. Hence, C, which is A union B, cannot be path connected. Okay, and this finishes the proof. All right. So we are done with the continuity. Connectedness also. The next thing we will do is applications of the stuff we have seen so far. And I'll start the first application, so-called Banach contraction principle, if you don't have any questions on the previous material. Do you have any questions on this material? Okay. Peki. Şimdi o zaman şeyden başlayabilirim. So there are 4 applications in the book. I'll cover 3 of them if I can, actually, if I have time, enough time. The first application is Banach contraction principle. Some applications. First one is contraction mapping theorem. Let me write. Okay. To state the theorem, I have to explain you what's a contraction mapping. Let me define it. A function f from x to x on a metric space xd is called a contraction if it satisfies the following. If uh, dxy, sorry, df of fy, alright, if there is a constant, let's say constant lambda less than 1, so that, okay, so that uh, dfx fy is always less than d, okay, lambda times dxy for all xy in x. So what's a contraction mapping? It is the following. There is a point, there is a real number less than 1, so that whenever you take 2 points in the metric space xy, the image of these points under the function f, so this is a symbolic picture. This is the point between x and y. This is the point between, this is the distance between f of x and f of y. And so the definition tells us the following. This distance is at most dxy times lambda, whatever lambda is. Lambda is a fixed real number less than 1, and therefore this means the function f just gets takes points, 2 points which are closer to each other. Okay, so whatever this distance is, the distance between their images is smaller than the original distance. How much smaller? Well, it is at least lambda times, it is at most lambda times the original distance. And lambda is a number between 0 and 1. Okay, it is strictly less than 1. So this function f then, if you start with 2 points, it takes them to points which are closer to each other. If you apply this again, it will take them even small, closer points and so on. Okay, and the theorem is this. Actually, okay, let me write down the theorem. Okay, let f be a contraction mapping on a complete metric space. Okay, so here I take X to be a complete metric space. Then there is a unique point x0 in X, so that this point is fixed by F. Okay, so there is a point in X so that F doesn't move that point, and moreover that point is unique. Okay, there is only one such point. uh, a point x in X with this property is called a fixed point. Fixed point of F. Okay, so this theorem tells us then, If you have a contraction mapping on a complete metric space, then this function is a unique fixed point, right? So that's the theorem. Well, how can we prove this? You see, from this explanation, you see that uh, f takes points, two points which are closer to each other, right? So if you repeat this, you will get